Hey, I wanted to do a deep dive into man-in-the-middle 6 and NTLM relay attacks, as these attacks have always left me a bit confused when I do them in lab environments, just because I felt like there was a lot of magic happening under the hood that I didn't really quite understand. So hopefully you watching the video will understand them a bit more as I've come to understand them in making the video. I'm going to explain this in a few sections, so let's get started with reviewing NTLM itself. So New Technology LAN Manager is what it stands for, and it's actually a very old suite of authentication protocols developed by Microsoft in the 90s for mostly authenticating to remote systems over the network. It's gone through a few iterations with its cryptography, but the core of it remains the same and revolves around these three messages: the negotiate message, the challenge message, and the authenticate message. We'll see a lot of similar but different acronyms in the space, so let's clarify these a bit. NTLM is both the name of the overall authentication suite and hash format itself, specifically an MD4 hash of the user's password, sometimes called the NT hash. Built on top of that are two challenge response protocols, NTLM v1, the older and weaker version using DES encryption, and NTLM v2, the modern version which uses HMAC and MD5, and adds a client nonce and timestamp to make it significantly harder to crack. The implementation that actually carries these protocols over the network, whether it's SMB, HTTP, or LDAP, is NTLMSSP, the security support provider that handles the three-way handshake of negotiate, challenge, and authenticate. Understanding this distinction matters for relay attacks because what we're actually intercepting and relaying is the NTLMSSP message exchange, and the underlying credential being abused is that NT hash. In the protocol version, v1 or v2, affects how difficult that captured exchange is to crack offline if relaying isn't an option. So before any communication takes place, it's worth noting that the client and the domain controller both have knowledge of the user's NT hash, and the server doesn't have access to this. So to start, the client initiates authentication with a negotiate message. The server generates a challenge block to send back to the client as a challenge message. Then the client derives an encrypted challenge block using the user's NT hash. When the server receives this challenge response, it needs a way to verify that the client actually produced a valid challenge response, and since it doesn't know the NT hash itself, it'll forward the parameters to the domain controller to verify. The domain controller will send the result back to the server so the server can determine whether or not to actually authenticate the client. The problem with this flow is that anyone sitting in the middle of this conversation can just pass the messages through to either side and end up with an unauthenticated session to the target. And this vulnerability sits within the implementation of NTLMSSP. So by default, NTLMSSP does not enforce message signing or binding the authentication to the session. And this means that a man in the middle can intercept the three NTLMSSP messages and forward them. NTLM v2 actually has the capability for integrity protection baked in. It supports signing and sealing at the protocol level, but the problem is that NTLMSSP negotiates these features during the handshake, and unless signing is enforced on both ends, a relay attacker sitting in the middle can just strip out or downgrade these negotiation flags, causing both parties to agree to an unsigned session. It's important to note that not all protocols rely on these NTLM SSP mechanisms for integrity checks. So for SMB, for an example, it solely relies on if the server has SMB signing enabled and enforced. So for these examples, I went ahead and disabled SMB message signing, as can be seen here with Netexec. And SMB signing being enforced by default has only started since the release of Windows Server 2025, so you're still extremely likely to be able to use this in real environments. Okay, so I have my AD lab set up here, and I have the four machines from the diagram earlier. So we have Windows 11, the Kali VM, file server, and the domain controller. So in the foreground here, this is the Windows 11 client, and I'm just going to start by authenticating directly to the file server. So that's hosted at .109. When we hit enter, we get a secret share. And now I'm going to switch back to Kali and start up in packet ntlmrelayx, with the target being the file server over SMB with SMB2 support and -I for an interactive SMB shell. So I'm going to hit enter. Now that is listening. And now we're going to change this .109 to .107 to target our Kali machine. So when we hit enter, we see all in the background here, we received a connection from .106, which is the Windows 11 machine. We are targeting the file server over SMB, and the authentication as the read account succeeded, and we started an interactive SMB client shell on localhost 11,000. So just to open that up, we get this interactive shell, and we can list out the shares. We see that secret share. We can use secrets, and we see the secret.txt file. So now looking over at Wireshark that was running on the side here the whole time, I have an SMB2 or NTLMSSP filter here. And if we scroll to the top, we'll see these 6 messages that match up with the diagram from earlier, where we have NTLMSSP negotiate, challenge, and authenticate. We can see scrolling down a little bit, right here is where we listed out all the shares, and right here is where we connected to that secret share. So if you haven't seen relay attacks work before, you might be a bit surprised about just how easy that was. Once we have the client authenticate to us, we can authenticate to anything in the environment that supports NTLM authentication. So there's still this dependency of them needing to authenticate to us explicitly. So this is where man-in-the-middle 6 comes in and removes that dependency, and it makes it happen automatically. Unlike basically everything else in the world, Windows prefers IPv6 over IPv4. And since many environments don't actually deploy IPv6, this leaves Windows periodically sending router solicitation requests out into the void in hopes that someday someone will respond with a router advertisement. So when the Windows client asks if anyone knows of an IPv6 router on the network, take a guess on what our man-in-the-middle 6 tool will respond with.
Well, of course I know him. He's me.
So yeah, our man-in-the-middle 6 tool will send a router advertisement packet. Now you might think, what's the big deal? It's telling a Windows system we're an IPv6 router. It's not really about that. It's about the options held within the packet according to the RFC. Specifically, I'm talking about these M and O bits within the router advertisement packet. It says when set, it indicates that other configuration information is available via DHCP v6. Examples of such information are DNS related information or information on other servers within the network. And we can see the use of these 2 bits in the man-in-the-middle 6 source code right here. It says send a router advertisement with the managed and other flag set, which should cause clients to use DHCP v6 and ask us for addresses. It also sets router lifetime to 0 in order to not advertise ourselves as a gateway. So we're back in our AD lab over here, and I have a filter on Wireshark for ICMP v6 and DHCP v6. I'm just going to run the man-in-the-middle 6 tool that I've been talking about, targeting my local domain. And immediately we send out a router advertisement packet. And this packet has the 2 bit set that we were just talking about. And we're just going to wait until our Windows system responds to this router advertisement, as it's on a periodic schedule to actually look for them. Okay, so it took about 20 seconds or so. It can take longer. But we see that in response to our router advertisement, we have these 4 DHCP6 messages. So the solicitation, and then we advertise back to the Windows system a DNS server of ourselves. And then Windows will use that DNS server to then query for WPAD, as you see all over here on the left. So whenever there's a change in the network stack for Windows, it'll send out this request to WPAD, which is just asking the network, is there any proxies available to me that I can automatically configure to use? And of course, we'll say yes, the proxy you can use is us. So we spoof the reply for wpad.ad.bert.local to point back to us. And the next time Windows will go to send a network request over HTTP, it'll send that request to us because it thinks that we're the proxy. And we are going to respond to them with, hey, you need to authenticate to us with NTLM. So that's how we get them to authenticate to us without the user interacting whatsoever. So I'm going to run through this again, and we're just going to run NTLMrelayx beside this man-in-the-middle 6 tool, and we'll see them work together for man-in-the-middle 6 to get the client to authenticate, and NTLMrelayx to then relay that authentication off to whatever server we want. So I reset the environment here, and this time we're going to run impacket NTLMrelayx before we run our man-in-the-middle 6 tool. So that'll be listening for WPAT authentication. We're going to run man-in-the-middle 6. And again, this can take a while to run. If you want it to go a bit quicker, you can restart the network interface on your Windows system. So I'm going to do that here. And there we go. We have a lot of traffic here. And I think I saw up here the same message. We have a new SMB client shell on localhost 11,000. So again, we can just log into that just to show you. And that's really it. So hopefully you learned a thing or two and feel a bit more confident when running these attacks. And let me know if I should cover any other attack like this. Thanks.